All right, we'll get started. Yeah, so this is going to be an introduction to graph neural networks for partial differential equations. But what I really meant by that is GNNs for PDE-based problems. So all physical problems driven by partial differential equations. So it's my first lecture, so if at any point you feel you don't understand something, just please feel free to interrupt me. Yeah, so I'm going to talk a little bit about AI for science, kind of explain the motivations, why we care about that, then a slight detour to GNNs, and then we're going to get to the meat of it and talk a little bit about GNNs for PD-based problems. And there will be a coding tutorial so that you can get your hands dirty with some code. All right, so AI for science. Yeah, so there has been a lot of work in the recent years towards applying AI to scientific problems, in particular with the rise of deep learning. So over here you can see the AlphaFold discovery, I think, which was considered as the breakthrough of the decade, if I remember correctly. So that's a work from DeepMind where they tackled the protein folding problem. So that was, I think it's not controversial to say, one of the biggest breakthrough in applying AI for science. And then a lot of other works came in. So this is a work from NVIDIA for nuclear fusion. It's a digital twin for nuclear fusion. I think it's called SJTC, if I remember correctly, gyrokinetic toroidal code. So that was applying AI to build a kind of digital twin because running the simulations is very expensive. It relies on PDEs, it costs a lot. So having a digital twin that is cheaper to execute is very convenient to understand the physics and what's going on. And then most recently, I would say over the last probably couple of months or probably the last year and 2 years, there's been a lot of interest towards weather forecasting. So this is the cover of Science. In fact, it's the cover from last month. And that was the results of a paper from DeepMind called GraphCast, where they tackled weather forecasting. So I would say one of the main takeaways is that they achieved a 10-day forecast of the weather in about under 60 seconds, where state-of-the-art solvers, which operate at a slightly lower resolution, take about 1 hour. So that was a real game changer. And then there's also been an equivalent with NVIDIA with the ForecastNet, which relies on the Fourier neural operators. So we'll talk a little bit about neural operators as well. So there's a lot of work towards this, and kind of the high-level idea and kind of the main objective behind all those works is the hope of having fast inference, so running machine learning model that can be faster than what you would get with traditional approaches that relies on mostly PDE solvers, and the hope of having zero-shot generalization. So if I can have a model that can learn from my data, learn the intrinsic physics behind the phenomena I'm studying, and then I can then apply that to data that the model has never seen. So that it's the hope of zero-shot generalization, applying those cheap models to unseen data. So that's kind of the high-level idea and the motivation behind that. So I'm going to talk a little bit about partial differential equations. So who's familiar with partial differential equation? Who has ever heard about that? Okay, okay, no. I don't think having a deeper understanding of this will super critical here. But yeah, in a nutshell, PDEs are central to describing kind of model different complex phenomena across science and engineering. In fact, most of the physical problems of interest that engineers and scientists care reduce to PDEs in many cases. So whether it's fluid dynamics, finance, structural mechanics, quantum mechanics, there's so many that I can't even remember all of them. But yeah, that's kind of the idea. Just to give you a few examples. So this is obviously related to CFD, computational fluid dynamics. So when you want to study the dynamic of fluids, for example, study the flow around the airfoil, or I don't know, like the flow of a river, among other things. PDEs can help you model that. Here it's another example I've been involved in. It's a very interesting example. related to seismic inversion. Who is familiar with seismic inversion? Does anyone have heard of that? Okay, so seismic inversion, for those who don't know, is mostly a problem of interest for gas and oil company. So the problem is you want to know where there is oil or gas. And so what you do is you can't obviously dive thousands of kilometers and then like kind of dig and see if there is oil or not. So what you do is you go at the surface of the earth or of the sea, depending on what you're looking for, and you trigger detonations. So that can be explosions, or that can be when you're on Earth, a big hammer that literally hit the floor. And the result of that is that waves will be sent, and they will be propagated through the different layers of the Earth's subsurface, right? And because of what we know from physics, right, we know that when you have a change of medium, you have reflections, so waves will be reflected. And a little bit further, you have receivers that will collect all those data that has been reflected. And then the question becomes, from those data I've collected, is there a way to infer the model of the Earth's subsurface? Is there a way concretely to know if there is oil or gas? That's kind of the high-level idea. And so this is this is called an inverse problem, and the dynamics behind is driven by PDE. So the dynamic is driven by the wave equation, so how waves propagate, basically. And that's an example. So that's a well-known benchmark for those problems. It's overthrust model, and this is the results of solving the PDE. So you can see you have a detonation over there, and then you can see the reflections, and then from those data you try to infer this model of the Earth. So they are everywhere, basically. I'm sorry for those of you who are not who don't like math, but I think that's going to be probably one of the rare equations in this lecture. So PDEs, what are there? Partial differential equations. They can be formulated like that. So think about an equation of that form. You have a solution U, right? And you have an equation that involves U and all its derivatives, right? So all its partial derivatives. That's why you have partial over there, right? It's a generalization of OD for those who know about it. And usually you take the highest order of the derivative, and that's how you refer to the PDE. It's a kth order PDE in that case because it goes up to derivative k. So here X is not necessarily special. If your domain is a spatiotemporal domain, if you discretize, if it represents like a geometry times time, your derivative can also involve time. So that doesn't necessarily involve only kind of derivative of your solution with respect to space, but also with respect to time, right? And usually to make that problem well posed, meaning to make that problem like, for that problem to be well posed in the sense that we know there exists a solution, we know the solution is unique, and it depends, plus other criterion, you usually augment that with boundary conditions, which basically means, let's say, you want to model the way the heat propagates in that room. You know that like over the wall, like the heat will propagate in a certain way. You can impose a boundary condition. You can say, when I solve my PDE on that room, on the walls, this should be the solution I get. And you can also impose initial conditions. That's in particular true when you have time-dependent problem. So if you remember that case, if you model that, you have a time evolution problem, right? So you have a detonation, and your wave will propagate. You know what's your initial condition, right? At the initial condition, you have an explosion, and then you solve the PDE to have the rest. But basically, you also often augment those PDEs with initial conditions. And those are examples of famous PDEs. So this is probably the most simplest PDE you can think about, Poisson equation. Just to give a little bit of idea of like where that type of equation is important. If you want to model the vibration of I think you call it a drum head, right? When you hit a drum head, that equation can tell you how the membrane vibrates. It's also used in plasma physics and in many other domains.
This delta?
Oh, sorry. Sorry. Yeah. This delta is the Laplacian. So it's the sum of all the second derivatives. So if you have a 3D domain and your solution depends on x, y, and z, that's going to be second derivative of x plus second derivative of y plus second derivative of c, right? So you have derivatives when it comes to PDE. That's the Laplacian operator. Another example is a heat equation. I mentioned like how to model the propagation of heat. So you have a derivative in time, dt, like the derivative of your solution in time, minus the Laplacian, which I've just announced, equals 0. That model can model the heat, right? That's what we call it, the heat equation. And then another example of famous PDE, but you have many others, is the wave equation. As the name indicates, it tells you how wave propagates. Waves propagate, and you have a second derivative in time minus the Laplacian. And you have many others. Navier-Stokes for fluid dynamics, Maxwell for electromagnetism. In fact, you can even couple Navier-Stokes and Maxwell, and that give you MHD, which some of you might know, for magneto-hydrodynamics, MHD. Schrödinger equations for quantum mechanics, Black-Scholes for finance. Basically, they are everywhere. That's the main message here. And the thing, the important thing to know about PDEs is that in the vast majority of cases, we don't have an explicit solution. We literally don't. We can't explicitly state what the solution is. And so that's why we use numerical methods. We use numerical methods to approximate the solution. And the reason for which I put solution with the S here is that sometimes we know that there exists a unique solution, sometimes we literally don't know. And in fact, if you go back to the Navier-Stokes equation, for the story, anyone that is able to show that there exists a unique solution of the Navier-Stokes equation will go home with $1 million, because that's one of the 10 biggest problems in math, and anyone that solves any of those problems earn $1 million, together with the Fields Medal, the equivalent of the Nobel Prize. So we don't know if there is one or more solutions in many scenarios. So you usually use numerical methods to approximate the solution of those PDEs. And the thing to know is, obviously, computers can only store finite amounts of data. So you can't, and those PDEs are usually defined on function spaces that are infinite dimensional. So what you need for those programs to be expressible on a computer is to discretize them. You need the discretization. And then here comes a plethora of methods. So you have the finite element method, which is one of the most commonly used methods for that. The finite difference, finite volume, they all have finite, because obviously it stores a finite amount of data. But many others, discontinuous Galerkin, spectral methods, can Google up that. And that's basically the results of decades of research. So those methods are well established. We know a lot of things about them. We know, like, in terms of the theory, the efficient way of implementing them on computers, how to run them on massively parallel architectures. They have been around for a while. And they are often accompanied with other things. So in the same way neural networks are the kind of the central element in machine learning, but usually for more complex problems, you have more than a neural networks, right? You have other operations in your machine learning models. In the same way neural networks provide the base brick, PDE is also the central element that is often augmented with other things. So in addition to the PDE, sometimes you have, for example, constitutive relations. So a good example of that is, let's say I want to study how a certain material can be react to certain forces. I have a PDE that tells me how to do that. But what I need is to understand how things like the stress and the strain relate, right? If I don't have that, I can't solve my PDE. So that's a constitutive relation. And in many problems, the PDE is just not enough. You need additional things, parameterizations or whatever. You also have, when you use those methods, a lot of questions that arise, like how do you actually solve them? Usually you end up with a problem solving a linear system of the size of the form AX equal B, where A is a huge matrix. And because this matrix is huge, you need to use to be a bit clever in the way you solve it. So you have advanced linear algebra techniques that come into the picture. And then also sometimes you may not just want the solution of a PDE, but you may want something related to the PDE, right? So if you go back to this problem, for example, if I want to know if there's oil or gas over there, what I do is I collect the data, and I don't just want the solution of the PDE, like, given a detonation, how does this look like? What I want is, given those data, what's the parameter of my of the Earth subsurface that if I were to solve the PDE would result in the data I've received. So it's the PDE, but you have an outer loop of that. You have an optimization problem that rely on the PDE. So often it's not just the PDE; it's more than that. And over the last, I would say, couple of years, obviously with the rise of deep learning, a lot of efforts have been put around solving those problems with machine learning. And here is a sketch of the kind of, not the pros and cons, but at least a few like main ideas that are often cited. There's more to that, I don't have enough space. But the thing, if you take PDE solvers, they are faithful models with theoretical foundations. And what I mean by that is, the theoretical PDE is known, is the results of sometimes like more than decades of research. But not just the theoretical model, even the numerical method is known. We know how, like if you were to increase the size of your problem, we know sometimes the order of convergence to which your error will converge. We have results on stability, we have theoretical warranties, so we have a lot of things we know about them, right? So they are kind of reliable. And they're also interpretable. They rely on physics. They're not just black boxes that rely on, that we're trained on some data, right? These theoretical foundations that underpin those models. And also we know that like there's no free lunch. So if you want to have a perfect solution, or at least something that approximates a perfect solution, you need to increase the resolution of your problem, which just means you solve your problem for more points. You sample more points when so over the course of discretizing your problem, you account for more, I would say, like points or data, although data is not accurate. But basically, as you increase the resolution of your problem, you get better accuracy. I hope I didn't confuse you. There are other ways by which you can increase the accuracy, but that's one way. And they also scale well with better compute resources. So usually, if I want to have a better solution of my problem or a more accurate solution, I can increase the high resolution, and I know how to parallelize this on massively parallel architectures. And more I have resources, more I can increase the size of my problem, and better my solution can be. But they have disadvantages, and they can be very expensive for large applications. So just to give you an example, so I did this when I was working with Total. Total is a French company for oil and gas, and they have at least they had at that time. Their supercomputer was one of the top 500 supercomputers. I think it was the first in terms of industry sector when I was there, and that tells you a lot on the size of the problem they consider. The problem they consider are massive. Yeah. Yes.
I want to know the usefulness of the 3D models in the industry. Is it something that they can trust more than using data-driven approach?
Yeah. So for scientific problems that are modeled by PDEs, we know that like if you do your physics correctly, that they reduce to PDEs. So that's kind of the base, the default model. The default way of understanding those models is solving a PDE. So data-driven approaches rely on data. They have a lot of advantages, also disadvantages, but they don't have the same foundation, right? You can't like usually when you have a solution, you don't really know perfectly how the model will behave when you change the data, when you push through data that the model has never been trained on or never seen. So it's a bit more heuristic. PDEs have theoretical foundations, right? They are the standard, they are the ways of describing those models. Does that answer your question?
Maybe they are still used in industry more than using maybe data-driven methods to make prediction.
So I don't know about all the different domains where they use that, but for sure for these particular examples, I know, for example, when I was at Total, they were interested in machine learning, but that was more a thing of like following. They were hyped, like understanding how useful they can be. But when obviously the results of those simulations will be used for decisions that in high-stake decisions, things that involve probably billion of dollars, right? You want to know, because when you have the results of this and you say, okay, well, my simulation tells me this is probably oil and gas, then you need to make a decision. Do I go and drill? If I drill, that's going to cost a lot of money, right? So when you do those decisions, do you want to rely on something that is theoretically backed up, right, that relies on centuries of research, or do you want to rely on something that may be very efficient but don't have the same foundations? So I'm not saying one is super good, the other one is not, but just that one thing that you can't deny to PDEs is that they have those theoretical foundations. They are reliable in that sense, which data-driven approaches usually don't have. But that's a very good question, because in fact I think that's the next point after that slide. Yeah, so they can be very expensive in terms of time, energy, also human resources, because there has been a lot of years of research on that. So the cost of having small improvements here and there are usually the results of a lot of research from researchers. So like there's not, I would say having big big improvements is way harder and would necessitate much more human resources, because it has been around for a while, it's well studied, and so on and so forth. And another con of those approaches is that it doesn't scale with data observations. So a very good example is weather forecasting. Weather forecasting, you have a lot of historical observations, but we know it doesn't scale well with data observations. Where data-driven approaches can scale very well with those data, because they are purely they are rely on data. And another con is they also often provide an incomplete description of the physics of interest. So one thing to know about PDE is that PDE modeling is mostly effective when it comes to modeling systems that closely follow a single fundamental law. But when your problem is more complex, when you have other physical phenomena that rise, or probably couple different physics involved with each other, it's less effective and provides it doesn't completely it provides an incomplete description of the physics of interest. It doesn't yield to a very accurate solution, basically. And a good example is what I mentioned about constitutive relation. If you want to study the way a material reacts to certain forces, you need constitutive relations. It's not just the PDE. You need something else. And so that's kind of for the different points for the PDE solvers. As for the ML for PDE-based problems, it can produce accurate predictions while being more efficient. That's at least the hope. There's also the hope for generalization, which I mentioned in the beginning. Like if I sacrifice some time to train my model on a large amount of data, and I can manage to get a model that generalizes well for the physics I learned, then that's very good, because then inference time will be way faster than solving the traditional approach where you solve the PDEs, which means once I have trained my model, the cost of tackling a new model, or tackling new data, is the cost of one forward pass for the machine learning model. Whereas for the PDE for the PDE solvers, it's still the same cost. You solve a PDE, which can be very expensive, and so on and so forth. So there is the hope that if you manage to get a model that generalizes well, it's much more efficient. And it can be more accurate in certain scenarios. Weather forecasting is an example, but we'll discuss this later on. And it also leverages data observations. As I mentioned, for weather forecasting, that's an example. There are plenty of other examples. But you have a lack of interpretability that's related to your question. They don't rely on physical theoretical foundations, in the sense that when you tackle a certain physical problems, if you don't inject any prior knowledge about the physics, then you don't have anything that tells you that surely, even if you apply your model to unseen data, it will behave the same way, or it will predict the physics correctly. It doesn't have the foundations that PDE models have. Yep.
So what about situations where you don't have a lot of data, and so you can't really fit any ML models, but maybe you still have some understanding of the physical phenomena, so could you still?
Mm-hmm. Mm-hmm. No, yeah, that's a good question. In fact, that's the next slide. So when you have knowledge at hand, surely intuitively you want to incorporate that knowledge in your machine learning model, right? You want to have that to incorporate that knowledge. Another word for that is you want to have an inductive bias. You want to inject assumptions about your model that would help predicting or tackling the task in a better way. So yeah, that's definitely right. And in the context of PDEs, when you're tackling problems that you know are modeled by PDE, then surely having this knowledge, incorporating this PDE knowledge, will be beneficial because there are many things. So first, it can lead to something that is more robust because if you're a purely data-driven model, when it's trained on a certain set of data, then let's say you then use that trained model on unseen data. How would it react? You don't really know, right? You don't really know if it will produce something that still is reasonable or makes sense. But if you can have some physical knowledge encoded in your model, then there's a hope that that knowledge can turn out to be very useful in those scenarios, right? So that's definitely helpful. It also gives you interpretability. It's not just a black box, right? It's a model that has some physics in it, right? So it's more interpretable in certain sense. In particular, if you can dissect your model and see like, okay, here's my physical knowledge I've put in my model. Oh, how now that I apply my model on unseen data, how is that physical, like, how does look like that physical knowledge? So if, let's say I have put, and we'll come back to it later on, but one way of doing this is that by putting the residual of the PDE, which just means you put the PDE. When you apply your model to unseen data, you can dissect your model and see, oh, this is my residual, and for unseen data, that physical knowledge, that physical constraint behaves very badly. Then you have a kind of way of inferring certain things about your model. You know that, oh, my physical constraint doesn't look right for that particular setting. There's also the hope of generalization because of what we have just seen. When the data you have been trained on might not be super helpful because it wasn't containing certain patterns, physics can help, and there's the lower data requirement. So this is exactly what you ask for. It's super logical, right? If you have prior knowledge that can help you learning a certain patterns, you have less requirements in the amount of data you would need to learn those patterns, right? Because you have another source, another income of knowledge. So this is referred usually as inductive biases, and yeah. The hope in those physics-driven ML approaches is you can benefit from the advantages of the ML approach while still maintaining some interpretability and mitigating the training cost. But one comment is, unlike other types of inductive biases, like geometric bias or relational bias, we'll come back to it. There are other types of biases, not just those two. Physics-driven inductive biases can be sometimes very difficult to implement. So when you have things like symmetry or equivariance or whatever, those things can be relatively simple to implement depending on your setting. But when you have things like, okay, a certain system of PDE, there are not that many ways. Well, theoretically, you can think of exotic architectures that would account for the PDE, but when it comes to implementing that PDE, it might be very difficult. Because the methods I mentioned earlier, the finite element, finite volume, they actually are... you actually have a stack of different layers, right? You discretize your problem, then you usually have a mesh. You need to have a certain way of assembling the certain quantity over that mesh. So there's a lot of knowledge and kind of engineering behind that might not be just easy if you want to do it. So this might be an obstacle. And this is what have led the existing approaches that incorporate physics to be for hard scenarios when you want to encode PDEs trivial. Like the only approach that incorporate the PDE that I know is physics-informed neural network, and what they do is that they just encode that in the loss with some hack to make that possible. But other types of physics-driven biases that have been implemented are much more straightforward, like symmetry and stuff like that. So that's why existing methods are often tailored to very specific use cases. But other generic methods do exist. So that's actually a work we have done to couple machine learning frameworks like PyTorch with PDE software like FireDrake to have a generic way of incorporating any type of physical constraint implemented here in FireDrake with machine learning models. And because in the same way machine learning frameworks like PyTorch have been optimized like to kind of devise certain architectures, train those architectures, it has been optimized by hundreds of engineers to do that. FireDirect is the equivalent. It has been optimized and designed for tackling PDE. So all the different difficult layers you would need to implement that I mentioned earlier, like discretizing your problem, the parallel aspect, how you dispatch your audio or data, the data related to your problem, all the different aspects that can arise, you get that automatically with FireDirect. So that's what we have been doing to couple that. And that's actually a very nice transition. Yeah, so you would see this red dragon on the top right quite often because I've also been involved, I'm still involved with the FireDirect project. So FireDirect is basically a finite element software. Finite element is one of the numerical methods I mentioned to solve PDE that provides a highly productive way to solve PDE problems in an efficient way. By highly productive, I mean in a few lines of code, in a way that is close to the mathematical formulation, so you just write down the math. And in an efficient way, I mean you don't really have to care about parallelism or whatever. Everything is done behind the scene, in the same way you do it in PyTorch. This is typically an example. So for those who are not familiar with PDEs, this might not be something that ring the bell in your mind. But this is basically a variation of the Poisson problem I mentioned earlier. So if you remember correctly, I mentioned this problem that modeled that modeled the vibration of the membrane of a drum head. This is the Poisson equation, a small version of it. And usually, so FireDirect is using the finite element method. And in the finite element method, you don't just take the PDE in the strong form. Strong form just means you have derivatives like this, right? The reason for which you may not want to do this, there are various reasons, but first of all, one is sometimes your solution are not even enough, don't even have enough regularity to be written without like this, basically, right? Because when you do this, you assume that, and I will be very short because I'm realizing I'm going into maybe slightly technical and difficult things, but basically writing this in that form like when you write that in that form, you already assume that your solution is has certain regularity to be written in that form. It's not always true, and so one way of doing writing PDEs and using the weak form. The weak form is just that you have integrals, you have what we call test function v, right? So like solving that PDE just means you find a u in this function space such that this equation is true for every v, small v, in big V in the function space. V is called the test function. That's called the weak form. And this is how you would do it in FireDirect. You literally just define your mesh, so that's your domain, omega, where your PDE is defined. You define your function space. Here I'm using a certain discretization, Lagrange. So this is an example of what I mentioned earlier in terms of like all the knowledge you need to implement those type of things. Like basically this is a discretized space. Because V is an infinite dimensional space, when you want to solve this on a computer, you need to come up with a space that is finite dimensional. It's a discretized space. Here I'm using Lagrange polynomials. I won't enter into details, but basically, depending on your problems, you may want to go with certain choices of discrete of spaces because you know that certain spaces are stable, meaning they will correct behavior to stay simple, and certain other discretizations are unstable, so they won't behave correctly. So there's all this knowledge. It's not just about, okay, I put my equation, I have my solver, and here it is. Like just to model correctly your problem, your discretized problem, there's a lot of knowledge that is involved. And so you define your function space, your function, your test function, and you literally write down what is here. So inner is the inner product, it just means the integral. Grad u, grad v, it's this, the gradient. U and v are there, and then you have a v over there. And then you just call solve, and it does the work for you. So that's pretty much it for at least the first part. Is there any question? Yeah.
So I want to know the difference of your package maybe Phoenix. Is it any different? Because I've been trying to use Phoenix for high dependent PDE that seems not easy for
depends what you mean by easy. Oh, sorry, I forgot to turn on the microphone. Thanks. Yes, it depends about what you mean by easy. But just before, yeah, you were right. Phoenix is an equivalent model. So FireDrake have different blocks, to be simple. There's one block that takes care of the symbolic. Those objects have a symbolic representation. When you write a gradient like that, we know that this corresponds to a gradient, right? So spatial derivatives. And with that symbolic knowledge, you can do a lot of things. You can automatically differentiate. You can do certain things with respect to the space when it comes to the mapping, to the reference element. Well, there's a lot of operations that get simplified. So that symbolic bit is common to FireDrake and Phoenix. So that's why if you look at Phoenix code, it would be very similar to that, at least for the symbolic part. One main difference with Phoenix, in particular recently, is that Phoenix don't support the adjoint problem anymore. Meaning when you want to solve a PDE, when that's all you care, Phoenix can do that for you, or you can also do that for you. But when what you have is a PDE constraint optimization problem, meaning you just have an optimization problem constrained by PDE, like the seismic inversion I mentioned in the beginning, you can do that in FireDrake again in a couple of lines, but you can't do that with Phoenix anymore. That's one difference. There are many more. I always forget about them. Yeah, that's at least that kind of delimits that shows one distinction. As for like it's difficult to implement time-dependent problems, what did you mean exactly? You mean like in the way to write it?
To find the weak formulation.
Yeah. So when you use the finite element method, there is some kind of a priori knowledge that is required. The first knowledge is how do you get that weak form? How do you move from your equation that everyone, when you talk about Poisson problem, you think about something like that, right? How do you move from that to something like that? It's a bit different because in the first equation you didn't have a source term f, you didn't have a u, but how do you actually move from the strong form to the weak form? That's one first knowledge that is required, and that's inherent to finite element methods. You just need to do that, to know that. Some problems are so common that usually you would just see how other people have do it, and you just literally copy paste it. But yeah, that's required. As for time, yeah, you usually use time integrator, like a Euler integrator, things like that. Again, that's kind of an a priori knowledge. So the software, what comes after, won't really add any difficulty with that, because it will literally give you a way to write down the exact same formulation. So there's no additional complexity. But yeah, if writing down that formulation is a problem, yeah, then there's not like you literally need to try to understand how this is done. But the software won't do that for you, right? Because that's the input. The input is that form. If you don't have that input, then it can't solve the problem for you. But usually for if the PDE you're considering is like one of the widely used PDE, usually if you just Google it and then Phoenix or FireDrake or whatever, you would find the weak form. You can find a weak form. It's very likely that you will find a weak form, and you can just implement that in Phoenix, and that can run. And I think both, so FireDrake, I'm sure, and Phoenix as well, have Slack channels. So usually just, if you have any problem, I would assume just jump in and then ask the questions, and it would help you.
What about the visualization of your solution? I know that for Phoenix you need to install another software.
What about the what, sorry?
Putting the result for your only can do.
Yeah, you can do it. In fact, we will do it in the notebook. FireDrake. I don't know about Phoenix, but FireDrake interfaces with Matplotlib, so it's the same interface fully. You will see it in probably about an hour. But yeah, you can do it. Yeah. All right. Is there any question on that first part? Amazing. Okay, so we will now do a small detour to graph neural networks. This will be more machine learning oriented. Yeah, again, if you have any question or if you feel I'm going too fast or too slow, just let me know. Okay, so graphs. Why graphs? Graphs are everywhere. I found this quote very, very nice. So it's a quote from a recent paper from Peter Velishkovich, which I strongly recommend to read. It's called Everything is Connected. It's a very nice insight to graph neural networks. And he said, so in his paper, he said, in many ways, graphs are the main modality of data we receive from nature. And that's very intuitive, right? In many things you observe, like many of the complex architectures and systems that operate around us can be represented as graphs. So here are a couple of examples. So this is a molecule. It's super obvious that they can be represented as graph. I think I don't need to tell you how you can map that to a graph, right? It's very obvious. It's a graph. Another thing is knowledge. How do you represent knowledge? One way to represent knowledge is to represent it as a set of triples of the form subject-object relation. So if you read on Wikipedia, you go on the Wikipedia page of Barack Obama, you read Barack Obama is married to Michelle Obama. Then you know that you can represent that as a triple: Barack Obama, subject, Michelle Obama, object, and then the relation is married to. And you can then represent that set of triples as a graph, right? Where the subject and object are the entities, so the nodes of your graph, and the edges of the relations, right? This is what is called knowledge graph. So for the story, when you have vocal assistants like Alexa, things like that, they have knowledge graph. In fact, I've worked for that, so I know. They have knowledge graph. So they crawl the web, things like Wikipedia, and they have this kind of aggregated form representation of knowledge. And then from that graph, they can provide knowledge-based answers. When you ask Alexa, who is the husband of Michelle Obama? Then it will say, well, it's Barack Obama. Things like that, right? So that's a graph. And another example is meshes. So when it comes in particular to PDEs, when you want to run certain simulations, what you do is you discretize, and that discretization comes with meshes, right? So it's a kind of a triangulation. So it's a partition of your domain, right? Here you have a triangulation of this domain, and this is a fluid problem. This is a picture from FreeFem++, another software I also was involved in. So you have a triangulation of your domain, and then you solve your equation on that mesh. So a mesh is clearly a graph, right? You have nodes and edges. I think you don't need to convince you about that. So they're everywhere. And so usually when you deal with deep learning problems, you have this kind of a toolkit. Like depending on the modality of your data, like what your data is, you want to go with a certain approach. Right? If your data is vectors, multi-layer perceptron. If it's grades, convolutional neural networks, right? In particular, images. If you have images, you want to use GNNs. If your data is sequences, recurrent neural network, or more recently, transformers. But as we said, because most of the complex structures that surround us can be seen as graph, then it becomes natural to say, well, what do I do when my data is neither vectors, nor grade, nor sequences? And it's a graph. And that's why I call them GNNs, graph neural networks. And the kind of high-level idea, it's analogous to CNN, right? CNN works by kind of leveraging a neighborhood, or like a neighbor pixels. For each pixel, you take into account neighbor pixels. It's kind of the same idea, but over arbitrary graphs. And so what you want is you want to learn to reason about kind of entities and the way they interact with each other, right? So when in this knowledge graph, you want to learn how things like, I don't know, like Michelle Obama and Barack Obama relate to each other, those kind of type of things. Although it's a bad example, because usually when you do knowledge graph, you do link prediction. So you want to know if there's an edge. So you don't know a priori that they are related, so that's a bad example. But when you have a graph, you want to learn the kind of a relation, how entities interact with each other. So what are graphs? So they're basically a collection of objects, nodes, or vertices. Depending on the application, you can use different terms. Plus the interactions between them, so plus edges. So they can be represented as a tuple like this, with the sets of nodes V and E the set of edges. And edge usually operate over a pair of nodes, pairs of nodes. So they're included or equal to V times V. And the set of edges can be represented as using an adjacency matrix, right? So you can construct a matrix where each row or column correspond to one of the nodes, right? And a given coefficient of that matrix aij would be 1 if the row I and correspond, if the node I and the node j have an edge in common, right? So if they belong to that space, and 0 if they're not. So it's an adjacency matrix. You have other ways to represent graph, like adjacency list, but you can represent them like that. And there are different types of graphs. They can be undirected. So, for example, if you look at that example, Barack Obama, Barack Obama is a politician of USA. So you have an edge that points to from Barack Obama to USA as like he's a politician of, but you can't say USA is a politician of Barack Obama, right? You would certainly have something else, like if you had another relation like USA had as President Barack Obama, but it won't be the same edge, right? So they can be directed or undirected. And they can also be weighted. You can have weight. I think that's fairly common when it comes to things like molecules, those type of problems. And they can be multi-relational. So you can have more than one edge per node. A good example, if I stick to this knowledge graph example, is what is called entity typing. So entity typing is when you have those graphs. One task that is usually done in information extraction is you want to associate each entity, each node, with a type. What is USA? USA is a country. What is Barack Obama? Barack Obama is a man, so that's one type. But he's also former president of the United States. This type of things. Yeah, so you can have more than one. In fact, I think I'm confused. Multi-relational is more than one edge. So the example I gave is wrong, but you could have more than one edge. I don't know. Like, imagine Michelle Obama was also the secretary of Barack Obama. He would have two edges, right? She's married. He's married to her, and he's a colleague of her, right? That's a better example. All right, and another thing to know is in graph representation learning, each node is also equipped with a feature vector, hi, which of certain dimensionality. I've tried to include in the slides references at the end, so just feel free to have a look and go if you want to learn a bit more. Okay, so before going further, what are the things you can do with the output where you get from a graph? This is again a picture from this very nice piece of paper that I recommend you to read. So you start from the inputs, right? And then your GNN will map that, and you will have, like, for each node, you would have on each node a feature vector, H, where that capital H is just basically all the feature vectors stacked with each other. And then once you have that, there are many things you can do. In fact, there are mostly three types of problems you can usually do. The first one is node classification. So imagine the entity typing example. You have Barack Obama. What is Barack Obama? Barack Obama is a man. He was also the president of the United States. So you classify each node. You associate each node with a type. You can also do link prediction. If I have Barack Obama and Michelle Obama, is there a connection between them? Yes, there is. They are married to, right? So these type of things. And you can also have graph classification, and I think that's predominant in things like in scientific problems around molecules. Like you want, given a molecule represented as a graph, to kind of infer a certain property, or categorize the whole graph representing that molecule. So there are many things you can do with it.
Sorry, the input into the GNN is like the graph itself, or?
Yeah, it's the graph. It's also it's a graph. You also have an initial feature vector that is then mapped. So each it's a bit of it because so each node, the x here also have the feature vectors, right? So each node will have the kind of a vector, a tensor, and then the GNN will update the value of those nodes. It can update. Yeah, it's not just about the nodes. Sometimes even edges have attributes. They have vectors because, for example, you study molecules and edges. You have different types of edges. But basically, you have kind of vectors, and the GNN will apply a certain set of updates of rules to update the value of that vector. And the main idea is using the neighborhood. So you have this notion like of connectiveness, like kind of the edges kind of facilitate having this locality constraint. When you want to know how this particular feature vector will be updated, you already know that this feature vector will be influenced directly by the things to which it is connected, right? So it kind of facilitates and enforces a locality constraint. In the same way for CNN, you would take into account the neighborhood pixels.
So you said that sometimes you can use them to, like, I don't know, predict an edge between two nodes. And in that case, like, the input to the GNN is the graph, what you know about the graph and the edges you do know, and then it comes out and predicts.
Yeah, so you can have the input of the graph, and then at the end, once you have performed your update on the node and potentially on the attributes, you kind of predict whether there is indeed an edge or not, or what is the type of the edge. Yeah,
You need to have the A, otherwise there's no computation to ask people like those I and J. So you need to have the initial connectivity defined.
Yeah, so you start with the graph, right? So with the graph comes edge connectivity. But yeah, I don't know if, because so I don't know if for link prediction, like when you don't know if there's an edge, do you populate them or? Yeah, I'm not sure about that. You start with the graph, but then I don't know how it is done. So I've actually been working on that, but in a relatively different settings where you don't. So I think it's how it works usually for things like, at least for no edge graph. You don't start with a graph. You start with a set of, you want to predict a set of triples. And those triples basically are just edges, right? And nodes, because in that triple you have the two nodes and then the edges that connect them. And once you have that list, you can form a graph. But I don't know whether you can start directly with the graph or not. That's a good question. I would assume if your task was to classify the kind of, you want to classify each link to each edge, then you can start with the graph because the edges and the edge connectivity is already there. You just have to kind of classify each edge. But as for understanding is there an edge or not, I don't know if you can start with the graph. And at least the way I've dealt with that is usually you don't care about, the graph comes after. Yeah, the goal is to kind of predict that set of triples that can then be ingested into an existing graph to augment it, or that can be used to form a graph if it doesn't exist. For non-edge graph, that's how it is done.
So when you say graph classification, you mean sub-graph classification? Like neighborhood, you want to classify some. Like what do you mean? So you're passing a graph, right, to the GNN,
yeah.
And then you say graph classification. What does that mean? Like,
so it means you will apply a set of updates on the feature vectors, and then at the end you will aggregate those all those features vectors over the set of vertices. So we'll take into account all the basically the nodes in your graph. You will take into account the feature vectors of all those nodes, aggregate them, push them through a f, which is a readout function, and then you will get something. So we'll classify your whole graph. I'm sure this can be applied when you have large graph and you want to classify a subgraph. Whether that can be applied, I don't know, but that's kind of the idea. The base idea is you want to classify the whole graph. So let's say you have a molecules represented as a graph, and then you want to know whether, I don't know, whether it's dangerous or not, or whether you want to answer a certain question about it, classify that molecule. That molecule is a graph, so what you want to classify is specifically the graph representing that molecule. And for doing that, you aggregate all the feature vectors, all the vectors on all the nodes, and then you apply a certain transformation, and you get an answer.
I see. So is when you say update and aggregate, so you're assuming there's some sort of message passing that's happening in learning.
Message passing will come later on. But while we are here, this thing is actually, we'll come to this, but the way you aggregate them, usually it's, so you do it with a permutation invariant operator. Because basically you want to get the same thing whether I have, I start with this node or this node, like depending on the order of the nodes or the edges, I want the results of my aggregation to behave the same way. So usually the way you aggregate is with a permutation invariant operation, like sum or min.
So it's like similar to like how octants happen in like graphical models, probabilistic.
In what, sorry?
Like probabilistic graphical models.
I don't know about probabilistic models. I don't know, but and that's how it's aggregated, right? You need to enforce a certain property. Yeah, so let's start with a very simple update rule. Let's say, so we have a J, let's say it's undirected, so I to J or J to I, it's the same thing. It's unweighted graph, so you don't have any weight on the edges. So one way to aggregate it, to kind of, to derive an update rule, remember update rule is what will, over the, so for each layer, you update the value of the feature vector, right? One way to do it is to just use the adjacency matrix. You just take the set of feature vectors. So Hn is the matrix that stacks all the feature vectors, and you have as many as you have nodes. And then you just multiply by the adjacency matrix. And when you do that, because adjacency matrix will just be one, like when the correspond, like each, like if a coefficient is 1, it means the corresponding, the node associated with the corresponding row and the node associated with the corresponding column have an edge. So when you will do that matrix multiplication, what you will get is something of that form, basically. So multiplying by the adjacency matrix is a way to having this sum over the neighborhood of the node for each node. Yeah, I have actually a bit spoiled you here. So and then you have H, and then you have W, which is this learnable matrix here, and you apply sigma nonlinearity in the same way you do it with neural networks. One problem with that is you're discarding the central nodes when you do that. So an easy way to fix it is to say, okay, my density matrix is actually A till weights A plus identity. So you account for the node I when you are updating the node I, basically. And so you then have, using that, you then can express this update rule node-wise, so at the level of the node. So for each node I, what you do is you take all the node in the neighborhood, you take all the node it's connected to, you multiply the corresponding feature vectors by this learnable matrix, and remember it will be the same for all the nodes, right? It's shared. You sum them, and then you apply that nonlinearity, and you get your new update rule. Fairly simple so far.
So is this like sort of applying, like using a multi-layer subtrunk, but you have this extra step of weighting by the adjacency matrix somehow?
Yeah, somehow, yeah, exactly. So the step where you kind of take into you multiply the adjacency is analogous to what you would do in CNN. It's just a way of like taking into account the neighborhood, right? It's kind of a relational bias, right? You know that each node directly depends on the nodes it's connected to, so you exploit that information. And then yeah, it's very similar to MLPs, right? Like that kind of looks like a linear layer, and then like it's a nonlinearity. And in fact, we'll see in a few slides that usually you also use MLPs in your update.
And is that different for each data point, the adjacency matrix?
No, the adjacency matrix is the same. The adjacency equates your graph, right? It's a representation of your graph, because it tells you how many nodes you have, right? It's the dimension, and it tells you what edges do you have.
Yeah.
So you have the set of edges, the set of nodes. It's a graph.
So like this knowledge graph that you're putting in, that you're training, I can imagine for different data points, different pages of Wikipedia, the graph will be like different sizes. It'll have different.
So I know there are approaches to what is called information extraction, where they operate with graph, but I haven't dealt with that, so I don't know how it behave in that way.
Yeah.
Usually, what I've been dealing with is you crawl a text, and your goal is to extracting triples, and you have those triples. And then usually internally for those large systems, you have additional filter. Like, for example, a country can't be married with the capital. Doesn't make sense. So you have this filter to kind of discard the triples that don't make sense. Yeah. And then once you have this filtered set of triples, you ingest it, meaning you augment the graph you already have with this kind of new subgraph that will
it has like a fixed
yeah, exactly. Yeah, you predict links, right? So link prediction, that's why it's called like that. But yeah, I think there are approaches that to use GNNs? I'm not familiar how it works.
Yeah.
Do they use just GNNs to produce those triples, or do they use GNNs like in terms of like the reason over the knowledge graph? I don't know.
Okay, so
Yeah, but yeah, that's basically a simple update rule. So we have fixed the first problem, and then there's the second problem, which is that when you multiply by the adjacency matrix, you may increase the scale of the output feature. So if you have two nodes, one with a small number of neighbors and another one with a very large number of neighbors, then your sum over here might result in larger values for nodes that have a lot of neighbors, right? So that's not something desirable, right? It can be problematic. And so one way to fix it, very simple way, it's to normalize. And that's how you get to a graph convolutional network. So you take the former update rule. So before we have a tilde time hn time this learnable parameter, and just normalize it. So you have, let's tii be the degree matrix. So it's the sum over for each row you sum over the column. So it tells you how many neighbors you have, and then you do this normalization on both sides. And that can be written pretty straightforwardly at the node-wise level. So that's your new update rule. So for each node, when you want to update a given node, what you do is you take all the neighborhoods, all the neighbors, you loop over the neighborhoods. You take all the neighbors, you do the same transformation, but here you normalize by the number of neighbors of I and the number of neighbors of J. Yeah, and so. Graph convolution networks, so they're simple, powerful. It's the most commonly cited GNN paper, so very popular approach. But they have one problem. It's not always they are not always problematic, but they have one problem, probably more I'm not aware of. But one obvious problem is that they don't directly support edge features. So if you're trying to study a problem where edges matter, they are not directly supported. They are kind of indirectly supported because I is related to its neighborhoods. So when you take into account the feature vectors of the nodes in the neighborhood, you're kind of taking into account, like, indirectly the edge, but not directly, right? Because those edges might have feature vectors, because you may have different type of edges that you want to account for. So that's limitation of GCNs. And instead, one could consider a more general edge-centric approach, where nodes send messages, that's what you said earlier, along graph edges. So you would have each node that would send a message. So for each edge you have a message. And so just this first point is nice because we have already addressed the problem. We're now compatible with edge features because when we send that message, we can actually compute that message to take into account the feature vector of the edge. Right? So you don't just take into account the feature vector of the nodes, but you can also take into account the potential feature vectors of the edges, and therefore take into account edge features, which may be very relevant for your problem. And that's the first step. So you form messages, and then once you have all those messages, which basically represent the information that flow on each edge, you can then aggregate them using permutation invariance, as we said, and then update the feature vector. And so you basically get the message passing neural network, which is, in fact, the original paper, I think, was focused specifically on a problem related to, I think, molecules. So basically a use case where edge features matter. And so what you do is for each edge, you compute a message, Mij, right? So it represents the information that flow from one node to another. And you compute that, and the way you compute that is you take into account, so you have the edge between I and j, you take into account the feature vector of I, the feature vector of j, and a potential edge feature, something over that edge, and you form your message, right? So j is an edge feature vector. And then once you have that first step, you have computed the messages, you aggregate the messages using a permutation invariant function, so here it's a sum, right? Whatever the order of the Mij, the results of that sum doesn't change. It's invariant to permutation of the nodes. And then using that the aggregation of messages and the node feature vector of I can then update the node I. And usually, and that comes back to a question, those two functions are MLPs, small MLPs. So you will have nonlinearity, but you can also have other things as well. And so that's how you kind of update the feature vectors of the nodes. So that's for message passing neural network. I don't know if I'm a bit ahead of time or not. I think it's been an hour. Do we want to have a break? Let's have a break. Yeah. Up to you. 5 minutes, 10 minutes? 5? Okay, perfect. All right, should we continue? Great. Okay, so I'm going to speed up a little bit because I realized I took too much time in the beginning, and there's a lot yet to come. There's also another book, so please just feel free to interrupt me if there's something that is not clear, because I'm going to try to go a little bit faster. So that's message passing neural network. So you now have MLPs. So what you're training is not just learnable weight metrics. You have more than that. You can have different layers. You want them to be small because that gets applied to all every time you do an update, whether it's an update to get the message or the node features. So there are small MLPs usually. Okay, so MPNN, message passing neural network, is the most potent GNN layer, at least when it comes to first order neighborhood architecture, meaning just taking into account the first order neighborhood. However, it requires storage of messages and can be prohibitively expensive for large graphs. That's one disadvantage. And so just to put into picture what we have just discussed, so that's usually how you do it. So let's say you have a graph, right? Every time you want to update the value of the node, the feature vector at the node I, here's what you do. You compute the message between hi and hj. For that, you take into account both feature vector, right? Makes sense so far. But also the edge feature vector. This wasn't taken into account in the graph convolutional network approach. That gives you a message, and once you have done this for all the edges connected to hi, you can then apply a permutation invariant function, here sum, that forms your aggregated message, and then you taking into account those messages plus the formal value of the node feature vector hi, you can then apply another MLPs or whatever model you want, and then get the update. And you do that recursively for so each layer you do that. And by doing this, you have kind of information that flows through your graph. Okay, so beyond MPNN, so graph networks.
What is the stopping criteria? Like, keep passing messages. Like, what would be the stopping criteria?
The stopping criteria. So at each layer you do that. So more you have layers, more you do that, right? So depending on the number of layers you have, that kind of dictates how many times you will propagate through your graph. So that's what dictates how many times you do it, and therefore, like, when does it stop?
It's actually a good question, because that's very interesting. Such like actually iteratively run GNNs. Where you actually have only one single layer even. So you don't learn like layer by layer different weights or different like 5 functions, but then you have only one layer, but you just like iteratively run it. And then you have a stopping criteria. Yeah. But it's like, it's very interesting.
All right. So beyond MPNNs, so graph networks. So there is this very nice paper from a team, I think was at DeepMind also mostly, on relational inductive biases. And graph networks, the reason I talk about them is that they are very commonly used when it comes to scientific applications. In fact, the GraphCast paper we mentioned about weather forecasting is using that. So I'm going to announce some concept that will then be used or discussed after that. So if you have any questions, just please feel free to interrupt. So this generalizes MPNNs along with other GNN architectures. So there are different architectures that fall into that setting, the graph network setting. So it's an expressive setting and easy to implement. And the way to see it, it's a graph-to-graph function approximator. So you take one graph, you return another graph. And with strong relational inductive biases, what that means is you take into account the relations between the different entities in your graph. The thing to keep in mind is when I say graph to graph, the output and the input, when you do that transformation, the output graph you get has the same structure than the input graph. So same edge connectivity, same number of nodes, but with updated feature attributes. And the difference, the definition of a graph is slightly augmented here. So it's not just a set of edges and vertices, but it's also, you also have a global attribute. So something something that kind of depends on the whole graph. So it's a global quantity that that can be updated, that will be updated over the course of the updates of the application of your GN graph network. So let this be directed. So directed means just one way. Like I to j is not the same thing as j to I. Attributed, meaning edges and vertices have attributes. By attributes we mean think about feature vectors or tensors. Each edges of vector nodes can have that. It's a multigraph, meaning you can have more than one edge between two nodes. And you have a global attribute, u. So let's consider this graph. So in what follows, this is the reference paper, if you want to have a look. So this is like how you do it. So there are many similarities with message passing neural network. So you start with a graph. Remember, a graph is defined by set of edges, set of vertices, global attribute. What you do is you're going to loop over the edges. Obviously, this is a pseudocode, but in practice, you have a more efficient way to kind of like parallelize this and so on. But the high level idea is you loop over the edges, and for each edges, you apply that MLPs. So well, that function that is usually a small MLPs again. And what that will do is it will take into account the edge attribute, so the kind of the feature vector or tensor of the edge k. It will take into account the two nodes involved in the edge ek, so the nodes, so the v. And here you have those small indices rk and sk. And what they mean is basically s means send, r means receive. So remember, we consider a directed graph. So it's not so when you have an edge from I to j, doesn't mean you have an edge from j to I, right? So to like those indices tell you who is sending the information. Well, who is who is like where is the edge starting from and where does it arrive, right? So you have those two nodes, and you have this global attribute. So this is very similar to that step, right? So for each edge, you take into account the two feature, the attributes of the nodes, together with the edge attributes. So there are some similarity, right? But you also take into account the global attribute, u, right? That's the first thing. So you compute updated edge attributes. You then get an update of the edge attributes. Once you have done that, you form the new set of edges, right? And what you do is you aggregate all the edge attributes. So the analogy of this, analogous the term of in the MP message passing neural network is the message. This is, you can see it as kind of a message. You aggregate all of that again using a permutation invariant function, right? So in the same way you would aggregate messages, and that gets you that quantity, right? Think about it as the sum of the messages, like if you have MPN in mind. And then you will now compute the update of the node, right? The way you do that is you take into account the sum of the messages, well, this quantity. Keep in mind this is equivalent, well, in the MPNN setting, this would be the sum of the messages. The node that you're updating, so this is the HI over here, so you have the sum of the messages, HI, and then the global attribute, right? So it's different that MPNN than just announcing how would that play in terms of MPNN, so that is hopefully a bit clearer for you. And then once you have that, you form the new set of vertices, the new set of edges using those quantities. And then what you do is you will then update the global attribute. So you have updated the edge attributes over here, the node attributes. You're now going to update the global attribute, right? And in order to do that, what you do is you aggregate the messages of the edge attributes, of the node attributes, and you use those two quantities to update the global attributes. I know it might be a little bit, a lot of details, but is that kind of clear so far? Is there any question? Great. And then once you have that, you've got a new graph. Because remember, a graph is a triple of set of edges, vertices, and global attributes. You have updated all those quantities. So it's a graph-to-graph mapping. It's a graph-to-graph function approximator, right? So those are pictures from the paper I mentioned. So you would start with updating the edges, Then once you have updated the edges, you update the nodes, right? U is the global attribute, and then you update the global attribute. And so the way that compares with message passing neural network is this is how message passing neural network look like. You take in edges, vertices. You first compute the messages, right? And then you aggregate them. This is the permutation invariant function. So this would be the sum in message passing neural network. From that, you get the sum of the messages. You use that to update the node, right? So using another permutation invariant function, and then you get you can apply a readout function to get the global attribute. And so that would be message passing. And now this is the difference. You can clearly see the difference when you update. Like in all the updates in the GN setting, you take into account this new global attribute, which can be anything. It can be a physical quantity you want to represent. It can be like pressure, or I don't know. You have these global attributes. First, you take into account that, and also you take into account the edge attributes when updating the global attributes, right? And unlike to MPNN, you're now also returning the edge attributes, right? So it might seem a little bit, maybe it's too much of details. I hope it's at least kind of clear the main steps, but that's kind of the difference. I'm taking time for this because I think many of the advances have been using this architecture, so it's important, I think, to understand them. And one thing that is good with the architecture is because it's a graph-to-graph function approximator, it kind of inherently promotes composition, right? Because you can now stack those blocks together. I give you an input graph, you can then apply a graph network that gives you another graph, etc., and so on. And this is a composition of GN blocks. And now another thing that is commonly done is, so you have this kind of stack of different GN blocks, and you can now also use this encode process decode. Just keep in mind that, because that will turn up a lot in what we'll see. So you start from an initial graph, you encode that, right? This is an encoder, so you're now in a latent space. Then you apply this set of GN blocks, and then once you have finished, you decode it, right? You get your decoded output, you get the final output. And another thing that is also often done is when your problem involves a sequence, in particular, think about time evolution problems. So you want to predict the weather, you want to predict the certain atmospherical quantities at different set of time. You can also have this structure where you stack the different GN blocks, like kind of one GN block mapped from a given time to time plus delta t, a new time step, and you stack that again and again, right? So you start from a graph at a given time, and then you use that to update that quantity and to get a new graph. All right. Is there any questions so far? Great. Okay, go on. So there are various other GN layers. So I think I was asked to also share with you when I think there are opportunities to have posters, in case you're interested. That can be a good opportunity. Like there are all those architectures. I'm sure they have been used for scientific problems. I won't discuss that. So there is Graph Attention Network from Peter Velishkovich. There's also this equivariant graph neural network where, from what I understood, the main idea is you're now also not only enforcing permutation invariance, but also rotation invariance. Because it turns out that for some problem, basically if you think about, I think it's molecules. If you think about molecules, the way I represent my molecule, whether I rotate it or not, it's still the same molecule. So I don't want my input to be changed by the way by rotation. So it's rotation invariance. GraphSage for very large graphs. I think we're talking about billion of nodes. GraphSage. Where basically what they do is instead of taking into account all the neighborhood, which would be expensive, you sample neighborhood, and that's how you update from your updates based on that. So a lot of other architectures that can be subject of a poster, like how those architectures have been applied to scientific problems. But also a very interesting other group, which I won't discuss because it doesn't fall into the topic of today's lecture, but why we are discussing GNNs for PD-based problem. Actually, the reverse has also been done. So it turns out that the way you update your node, right, the way you perform your node can be efficiently represented via PDEs. In fact, it can be represented via a heat equation, right? Because it's kind of very intuitive. Heat propagates in a kind of smooth way. So there's a lot of research on that. There's this graph neural diffusion paper, very interesting, There's also graph neural OD. Might be worth having a look. So there are other layers which I won't discuss here. So now let's move to the kind of the meat of this. We have done all this setting. So let's see how it has been used for PDE-based problems. So I will kind of just go through a couple of papers that have been done towards that. Some of those papers, like this one, doesn't really care about like the PDE. They don't encode the PDE anywhere, right? Some of those papers we have used the PDE to generate data, but it's not, the PDE is not there, but it's a PDE-based problem, right? Because they're modeling a problem that can be represented by PDE. So this is graph networks, the architecture we just mentioned for particle-based simulations. It was a paper to get as well. I think it's from DeepMind as well, where we discussed. They start from this the particles in this form. They construct the graph because particles are just a set of points. You don't have edges, so they construct the graph. They encode that. Remember, encode, process, decode. Then they apply different layers of graph networks to kind of pass the messages, right? You have the edge attributes, the node attributes. They pass messages, and then they decode the output to get the new position of the particles. Very nice. Also simulations. Look at the paper. So that was for particle-based simulations, and this is one that also was done by the same team for mesh-based simulations. Remember, mesh are kind of ubiquitous when it comes to modeling PDEs using numerical methods. So so they've done mesh simulation. So for example, this is the traditional way of doing something like that would be like you solve Stokes and Navier-Stokes, and with a numerical PDE solver using numerical methods, and then you get that. So because like they operate on graphs, including meshes, they can do that. They can also do all the fancy things like the dynamic of a flag, like submitted to some wind forces, the way it moves. Very, very nice. And again, they use a graph network. I won't enter into detail. One thing that is kind of very interesting in that paper is when they apply the graph network, they get an output, right, P, and actually the quantity they're looking for is Q. And what they do is they say, well, okay, my P is kind of is kind of a derivative, higher order derivative of my Q. So what I do is I will use a time integrator, something like Euler, if you're familiar with it. If not, never mind. And they use the output to compute the Q, right, using this time integrator. And the reason it's interesting, it's a kind of like, it's kind of an inductive bias, right? If you are studying a certain dynamic and you want to predict the velocity, and at the end you want the acceleration, if you know the acceleration is the derivative of the velocity, and you kind of encode that, it's kind of an inductive bias that you're injecting. You are kind of injecting some prior knowledge about your system. So that's interesting, and then they get the new positions of the cloth, the flag here, or the flag. I think it's this is a cloth. It's different from this one. All right. So graph networks and what I've just shown to you is more about I've got a graph and I want to leverage the relation between the different entities, and then I perform my updates, and based on that strong relational inductive biases I have in my architecture, I kind of by feeding my model with a lot of data, hope that I will get something that learn the intrinsic physics that I'm studying. This is one approach. I think another line of research more towards scientific computing, so people that have a PDE background, I think, that have come up with different approaches. So there are two main ones. I won't enter into too much details, but the first one is very, very popular. It's called physics-informed neural network. I mentioned it in the beginning. And basically, I want to solve a PDE, so a PDE that depends on space and time. I want to learn that mapping. Give me a position in space, a certain time. I give you the solution. And what they do is they train an architecture, neural network architectures that takes as inputs both, like positions and time. And they train on that, right? And the output is you, right? So it takes this as input in your network and it outputs to you. And they encode physics, and that's the only, one of the only approaches I know where they specifically encode the PDE. What they do is when they construct the loss, they encode the residual of the PDE. What is the residual of a PDE? When you have a PDE, you can express it as something like f equals 0, f of u, where u is my solution. This f is called the residual, right? Now, when you add the norm of that into the loss, you're effectively incentivizing the fact that your system needs to be trained in such a way to satisfy that, because the purpose of training is to minimize the loss. If you minimize the loss, you want that norm to be close to zero. If this norm tends to zero, it means your residual is zero. And if your residual is zero, you're satisfying the PDE, right? So you're encoding that physical prior knowledge at the level of the loss. So that's what they do it. And now, computing that residual is actually requires a lot, right? In finite elements, you would do a lot of things. But the trick here is, because they take as inputs x and t, in order to compute the special derivatives, they just need to do gradient of the outputs of my network with respect to gradient of the inputs. And PyTorch knows how to do that. So they don't have to go through the pain of doing a finite element assembly. You have a mesh, and then you discretize and all of that, because they just say, well, my special derivatives will just be derivative of the output of my neural network u with respect to the part of the input that correspond to x. The time derivative will be the same thing with respect to the part of the input that correspond to t. And that's how they can specifically encode the residual of the loss, compute that quantity. It's a priori applicable to any arbitrary neural networks, including GNNs. That's one approach. Another approach that is gaining a lot of popularity, probably becoming the most popular approach, is operator learning. And basically it says, well, instead of learning one instance of my PDE, like from x and t, give me the solution, I will learn a family of PDE. So let's say I have a PDE that is parameterized by some parameter, lambda. I want to learn the mapping from lambda to the solution of the PDE. Very simple example. Let's say I want to model the solution, the heat in this room, and I have source terms. Those source terms can be heaters, radiators, at different places of the room. I want to learn the mapping that goes from my source term, associated with the position of the radiators, the number of radiators, all of that, to the solution, the effective solution of the PDE for that setting, right? I want to learn that mapping. It's much harder, right? Because you're now learning not a single instance of a PDE for a particular lambda, but you're learning the mapping from any lambda I want to get my solution. So it's called operator learning. And that operator can be anything: source terms, boundary conditions, constants, whatever. Imagine, if you want to do fluids, you can imagine you want to learn a mapping from Reynolds number from the solution of the corresponding Navier-Stokes equation, for example. And this is compatible with the physics-informed setting. So this kind of setting, when you have the residual in the loss, in fact, it's called PNO, so physics-informed neural operators. And this is this paper.
Maybe you're going to get to this, but how do graphs come into play here?
So for the pin part, it's something that operates at what do you take as input and how do you construct the loss. There's no strong assumption of not much assumption on the neural networks. That part is pretty flexible. So you could, for example, use a graph neural networks for that part, right?
But so here your input is this x and this t, right?
Yep.
And x is a vector, or is it, yeah?
Yeah. So it will be all the spatial coordinates you have sampled from your domain. So you're sampling points from your domain, and you are and then for that will constitute the input x of your model.
And so if in certain settings that might be a graph, and then you just use that as the graph in the graph.
Yeah. So once you have that, you could take that as input and then use a graph after that. Sure, there are many ways of doing it. I don't know exactly how it's done in practice, but then you can map this to a graph. I would imagine you could have, for example, the nodes of your graph being the different positions, and then selecting the edges based on a certain criterion. I don't know. There's some work on that, but I'm not familiar with it. But the main part is because you're not because in between you have your model, there's no a priori restriction on what that model can be.
Okay, but it's not that GNNs are necessarily particularly suited to solving PDEs. It's just there.
Yeah, yeah, exactly. That was mostly a way of saying this is how you can encode physics.
Okay.
Yeah, there wasn't this is particularly suited for GNN. It was more we know because of what we have discussed that it's important to incorporate physics. It can be critical. Maybe there are some cases where it's not that important, but it can be critical, and so that's one way of doing it. Yeah, and it composes with GNNs. All right. Just one stop to like time evolution and how you actually handle that. So there are different approaches to that. Okay, I'm going to speed up a little bit, but okay. So one approach is, remember, I said you have this operator learning where you map from one parameter to the solution of the PDE. So the first approach is the neural operator approach. So give me an initial condition, and I directly give you a construct a model that maps from that initial condition to a certain time. For example, give me the state of the weather yesterday, and I will construct a neural operator that give you the solution of that like 6 hours later, for example. That's the neural operator. The second approach is the autoregressive model. So you generate. It's what basically they do with GraphCasts and with the graph networks approach. You stack blocks and you have a model that maps from a time t to t plus delta t, right? To a certain time to the next time step. Autoregressive approach. Now this might be very unstable because if you make a small error, if your model makes a small error to predict one time step, then you're suddenly stacking that and then your error propagates. You're kind of accumulating errors and that can be problematic, particularly if you are interested in a system that is chaotic, where we know that small differences can have a huge impact. And so an intermediate approach that was done in this paper is temporal bundling. And what you do is you kind of do autoregressive, but instead of predicting one time step, you predict a bundle of different time steps synchronously. And you therefore reduce error propagation, and they came up with a trick that also reduces inference time. So you improve stability. I'm going to accelerate, go faster. So yeah, this is another example of message passing neural networks, neural PD solvers. This is the paper that did temporal bundling. And what they did is they considered PD of that form. This is known as conservation laws. Many PDs fall into that. And they use the encode, process, decode approach from the Battaglia paper, so from the graph network paper. But instead of using a processor that is a graph network, they use a message passing, and message passing are type of graph network, but basically they specifically use this message passing instead of a general graph network. But yeah, message passing are an example of graph networks. And this is the form of the thing. The F is the H, and what we have seen is the feature vectors, and the U is the solution, right? So they from a time k, k minus capital K, they produce a rollout of K step, capital K step, and they take into account positions to form the message, and that's how they update the feature vectors, and they take into account additional information about the PD, like constants or whatever. Okay. So one application, I think I'm going to go very fast here because we don't have time and we have a tutorial. But yeah, basically that was about weather forecasting. Weather forecasting, as I said, is a nice application for ML. There are a lot of things that makes it very suited for that. And this is the GraphCast paper. It's the one that I mentioned earlier for weather forecasting, where they... I think it's from the team that did the graph network thing. So they basically apply the same thing. They use a graph network. They have an encoder that maps from this grid to a mesh, and then they have the processor that operates at different mesh resolution. And the reason they do that is to take into account long range dependencies and also to reduce the inference time. I think the initial grid was about 1 million points. This one is much less. I can't remember how much. And then once they have processed, they have the decoder that maps that from the Cartesian grid. And then they produce by stacking that model. They can produce long rollouts. So I think each block predicts 6 hours forecast, and by rolling this out, I think they were able to produce a 10-day forecast in under 60 seconds, which is very fast. All right. Lastly, a few remarks. So when it comes to comparing machine learning and PDEs, there are a few things that I think, in my opinion, we should be careful of. Many often, what you would see, and it's totally legitimate, but what you would see like pictures of the results of the machine learning model, and it looks good. So you think, oh wow, it looks good. But when you look at the relative error, it's pretty high compared to what you would have in traditional solver. And that kind of compromises the comparison, because when you say, oh, look, machine learning is much more, like my model is much more efficient than traditional solver, you also need to take into account that error, right? Because if you ask your solver to just solve for that particular tolerance, it would be much faster. So this is often not done. Also, it's a different paradigm when you do machining. You also have the training time, whereas when you solve a PDE, you don't have this like training and then inference. You just have solve. So it's important also to have that into account when you want to compare efficiency. Benchmarks are difficult because generating data is expensive. There's a lack of data sets to have consistent results to compare with. And yeah, ML approaches often shine in scenarios where the above constraints are mitigated. That's just like my personal opinion. Some people may disagree with this, but yeah, weather forecasting, because you can leverage historical data, you have 40 years of historical data, like that's just perfect, which you can't leverage when you do traditional numerical weather prediction. So you do have the data set. As for the tolerance, they were able to get something like more accurate than the existing model. And yeah, that's pretty much it. And now we will go to the tutorial. Yeah, you need to scan this QR code to get the tutorial. I think you have I don't have a Mac, but I think there's an option to kind of like take the link from the phone to the laptop, which I don't have with HP. But otherwise, I would assume you can just send it over by email. And yep, let me just know when you're done. What you should see is something like that. Yep.
You show the code.
QR code.
Ah, sorry.
Should we create a copy, or are we directly on?
It was my first time using Colab. I just authorized edit. I don't know if this copy is made automatically or if you need to do something on your hand. Was I supposed to do something or?
No, but if we make changes here, will it change on yours?
I don't think so. I think it automatically makes copy and dispatch. I think I tried locally on my phone. Hopefully I'm not wrong. Is it okay for everyone? Does everybody manage to do that? Okay, so the first thing I'm going to ask you to do is execute the first cell. What this is going to do is install FireDrag, install FireDrag, do a lot of like dataset download and import libraries. Like the FireDrag import might take 1 to 2 minutes, so just run that so that it can run in the background, and then we can go through the beginning of the notebook together just to see what it's about. Did everybody manage to at least run that cell? All right. Running. Okay, so I can go to I can start the notebook. Does anybody need help or?
It says the file is updated. Refreshing.
Okay, just to refresh. If it persists, just let me know. Yeah. So while this runs in the background, let's go further down. Oh, it finishes for me. It finished for me. Okay. So this is what we want to do. So this tutorial is about kind of doing operator learning, where we want to learn the mapping from remember, we have a PDE that is parameterized by parameter f. So f is the right-hand side. And we want to learn the mapping from that right-hand side f here to the solution of the PDE. This is the Stokes equation, for those who are not familiar with this. This is a simpler version of Navier-Stokes. Navier-Stokes are ubiquitous in CFD, computational fluid dynamics problems. And this is a simpler version in the sense that it's linear. Navier-Stokes are very hard, they're not linear. And it's time independent, so you don't have notion of time, right? It's a steady equation. So you get this minus Laplacian, so this is Laplacian, sum of second derivatives, this is the gradient, and this is the divergence. So we want to learn the mapping from f to sol. Give me a right-hand side, a source term f, and I can give you, my model can give you what's the solution for that. And the solution here is a tuple of two things, the velocity, u, and the pressure, p. Okay? Forward. And so we have a geometrical domain. So I will ask you now to run the second cell. And this is the domain we will study. So this is, if you remember the slide on this graph network applied to mesh-based simulation, that was kind of it was doing this kind of example. It's a classical bench test case in CFD. So we'll study the flow that goes from that boundary, right, in that direction, and that will go around the cylinder, right? We want to study that. How is the PDE solution of that?
The point's just randomly sampled.
No, this is
loaded this Stokes cylinder, but
yeah. So this is a mesh. It's
the mesh. The points were just randomly sampled. Like they're not even unless it's an optical illusion. They're not even in like XY space, are they?
No. So the construction of mesh takes certain things into account. I don't think it's randomly simple, but this was basically sampled by making sure that you have a kind of homogeneous size of triangles,
Okay.
right?
Yeah. There's a circle there.
Yeah, exactly. You have a lot of notions when it comes to mesh, like conformant and a lot of things. But basically, it was generated in a certain way that you kind of have an homogeneous size of triangles.
Yeah.
All right. Did everybody manage to learn that? Amazing. Okay. So what we will do is we will use Phi-Drake. So this Phi-Drake will generate we'll solve the problem in the first instance just to see how it looks like. So here I'm defining the math of my problem. I have boundary conditions here. This is the function space. There are a lot of things. We don't need to go into details. Also, we don't have time. And then I will run the next cell that solved the problem. So this cell, will solve the problem, right? So I've defined my problem here. This is my variational form of my equation. I put that here. I put the solution, my boundary condition, and that will solve it for me. So far, so good. Amazing. I'm then gonna run this helper function for plotting. And I think someone asked me in the beginning about plotting. So this is how you would plot in Phi-Drake. Like you literally use the same thing that you use in Matplotlib. You do trip color, streamline, the same thing. The only difference is that you import that from Phi-Drake, because Phi-Drake has a wrapper that kind of interface those command with the finite element functions and what it means to be a finite element functions, how you represent them, and so on. All right, then I'm gonna look at I'm gonna run the next cell, and you should see a beautiful image, or beautiful images, hopefully. I haven't done anything wrong. So because this is running on Colab, I took a low resolution. Like the mesh you saw is a low resolution. Usually you would run that on a much higher resolution. So this is the solution I get. So this is the streamline, this is the flow. So you have the flow entering this side. It goes towards around the cylinder and then continue its way all the way to the exit. So this is the x velocity, the velocity in the x-axis, and this is the velocity in the y-axis, right? So the velocity is a 2D vector, right? Because you have a 2D domain, you have the velocity that's in the x in the horizontal direction and the vertical direction. And this is the pressure for that particular problem. All right?
But so why does the velocity in the y direction have this shape?
So this characterizes the velocity in the right direction, and so when you get close to the cylinder, you go around you basically go around to overcome it, and so I would assume that here you would have. So something happens around that cylinder because that's where you have the movement. Now this is negative, positive.
It seems like when it goes on top, it goes faster at the beginning, and when it goes below, it goes slower.
Yeah, there's something.
I think it is the directed velocity in the y direction.
Yeah.
0 to begin with.
Okay.
And then it increases.
Because it's going down, it's going in a negative direction. So.
Yeah.
I see. Okay.
Yep.
That makes sense.
I always get confused with those type of things. And that's you get the pressure. Again, things happen when you get near to the cylinder. Okay, so one thing we want to do here is we want to have physics-driven approach where how ML model takes into account physics. And what we'll do is we'll do the exact same thing that PINs does with a difference. We're going to assemble the residual. Remember the residual form? That's what PIN does. We're going to create that function that takes in the function sum of my PDE, the right-hand side, and it assembles the residual, taking into account the boundary conditions, right? So give me a sum, give me a f, and I assemble you that, right? And then we're going to create a wrapper, a PyTorch wrapper that represents that, right? Why do we want to do that? Because we want to do that. We want to use that inside the machine learning model implemented in PyTorch. So we want that physical constraint to be accessible in PyTorch. That's what I meant by like there are generic ways of doing it. This interface, like this torch operator, enables you to incorporate any physical constraint implemented in Phydrake, so residual of a PDE or whatever. You can incorporate it in actually one line of code into form a PyTorch object that you can then use in training. Okay, we have 10 minutes left, so I think we're going to speed up. Okay, what we want to do, we want to have encode, process, decode. It works well, as shown to be successful. We want to have that. Encode and decode will simply be a linear layer, a simple linear layer, right? You map from an input dimension to the latent dimension from the encoder, and from the latent dimension to the output dimension. So we'll start by doing this here. Now, exercise, this is the encoder, right? And this is the decoder. You need to do those two steps. In fact, you needed to do that originally, but because we have 10 minutes, I will do it quickly. Do you have any idea of how we can do that? So it's basically the same thing, except that encoder maps from the input dimension to the latent dimension, and decoder from the latent dimension to the output dimension. And yeah, but basically you just copy paste this. Do it here, call it. So that's gonna go from latent dimension to output dimension, and we call that decoder, right? And then we will just return, so that forward implements the forward pass of that decoder model. We'll just apply that decoder to the feature vector h, right? Which lives in the latent space, because remember, we are decoding, so we are operating on things that live in the latent space that have already been encoded. So far so good. All right, everyone is on the same page on that. Amazing. Okay, that's the easiest path. Encode, decode. I now want to do the processor. This is what we're gonna do. Very similar to the message passing neural PDE solver. This will form my message updates, right? I will take to update the message, to form the message between I and j. Will take into account hi and the difference between both hj and minus hi. So let's start with this first thing, and what I will do is I will make that a little bit coarser so that hopefully I can still manage to see it. So first of all, those two, as I said, those two operators are usually small MLPs. This is what we do here. We define the message MLP and the update MLP, multi-layer perceptrons. And when we're going to encode the first message, right? So how we do that? We have a function in PyTorch geometric, that's what we use, that is called message. And the objective of that function is to implement mij, right? So I will literally copy paste or do what is over there, right? So what I will do is I will concatenate, I will form a message M that will concatenate, so torch cat, hi, because that's what is over there, which hj minus hi. So hi and hj, right? Hj minus hi, okay? And the entry, the dimension of the entry is, the first dimension is batch, the second is the number of features. So this concatenation will happen on the last dimension, which is why I will add here dimension -1 to say it is at the last dimension that you concatenate those two things. And then I will simply, on that message, so this is I concatenate both, apply my MLP, right? So I will use the MLP I have defined above, so called message MLP. I will zoom in a little bit. Self message MLP on my M, all right? So this is the message. I'm going to speed up a little bit, and then the update will just take the sum of all the messages, the mean to be correct, and hi. Now the thing you may have noticed is that over here I specify the agor keyword argument, and what that means is it tells the message passing class, how do you want to aggregate the messages? Remember, we want to use something that is permutation invariant. When I say mean, when that class message passing will call the message class, the message method we have just implemented here, it will use all the MIJ, it will take all the MIJ and aggregate them using what I will have specified here. So it will aggregate to form the mean, right? So the mean is already passed to the updates. So the message that you see here is the result, it's the mean. It's the mean of all the messages, right? So it's this. And now want to concatenate this and this to feed the other multi-layer perceptron. So we'll do the same thing, what it said, torch cat again. What I will do is I take the H, the message, and I concatenate in the last dimension. And then once I'm done, once I've done this, I apply the multi-layer perceptron. So I do update MLP on Z. All right, is that good so far? Yeah, I think I should have organized my better because yeah, this it was initially supposed to be an exercise, but yeah, hopefully you still get some useful things out of it. Yeah, so this is just we just concatenate and then we apply the MLP to form that. So far so good. So we have the encoder, we have the decoder, we have the processor. Now we will form the model that takes all of that into account. So we take a PyTorch module and we apply that. So we have encoder, it's the class we defined earlier. We have this module list that will just stack all the message passing neural network. Here we will stack it with a certain number of layers, right? And then we have the decoder, right? And the for method is apply the encoder. Okay, we'll zoom it a little bit. Apply the encoder. Apply the processor, the message passing neural networks n times, where n is the number of processor layers, and then apply the decoder. As simple as that, right? Okay. So I have my model, and I will now train. So I load my data sets. All right. This is how I evaluate the error. Remember, I want to learn the mapping that takes the source term f to the solution, f to the solution. So I have my model that takes f. It takes edge index. Edge index is the adjacency list. Sorry. So it represents the graph, right? And that will call the encoder, processor, and decoder. And then I compute my error. I compare the output. I compute the L2 norm of the output with the exact solution. This is evaluate.
And the exact solution is what you've got from
the batch, from the dataset. Dataset contains a tuple of f and u exact.
Okay.
And I predict f to prediction of the solution, and I compare that with the exact solution I have for my dataset. Very simple. Super.
Just thinking like bigger picture then. So this exact solution is obviously not possible for a very complicated situation. Like
yeah, the whole point is those are the data you train on. But once you have something that has learned on those type of data, you hope that you have learned the physics. And if you have any new setting, you just apply f. You don't know the exact solution, and you take the output as a good surrogate for that.
As in, you could apply this model to like if you change the boundary conditions or something. Or is that the idea? Like,
so this model is parameterized by the source term.
Okay.
So it was trained with a certain set of boundary conditions.
Yeah.
But the boundary conditions are not taken into account in the inputs. So if you were to change if you were to take into account new data, you would get new f. But if you also get new boundary conditions, you're now applying your model on unseen scenarios, right? Don't know how it will behave. Might work well or not. But it's not explicit.
Yeah, okay.
Like the change in boundary condition is not explicit because they're not specified as the inputs. You didn't learn the mapping from boundary conditions to the solution.
Yeah.
All right. So this is the loss, remember? So we will compare the solution with the exact solution, and we will have this physical constraint. And the physical constraint is what we implemented in Phydrake, right? It's the residual, right? So as the loss get minimized, we want to obviously have those two terms to go to zero. So the training will update the parameter of my machine learning algorithm so that the loss goes to zero. And loss going to zero means that this particular term is also going to be obviously tend to something that is very small. And when you get when you get this term to that becomes very small, 10 to 0, it means your residual is 0. And if your residual tends to 0, if your residual tends to 0, you solve the solution. Because the definition of f is that if you find a u such that f of u is equal to 0, you have solved the PDE. U is your solution, right? So f is given, but u will be the prediction of my model. So every time I get an output, I inject that into the residual and I see what's the norm. If the norm is close to 0, then probably I'm very close to the solution, right? So this is a physical constraint that is encoded at the loss level in the same way that it's done for pins.
And this alpha controls the weight.
Yeah, it's a regularization term, so you have alpha. Yeah.
And how do you choose that? Like,
arbitrarily, you can tune that arbitrarily. You kind of balance between the data you have from your data sets and the physics you want to encode. It's a compromise. And one thing I wanted to emphasize, so this is different than pins. I don't need to have as inputs x and t. I don't need that, right? Because with pins you have x and t because then you can assemble the residual, right? Because it's just the gradient of the output with respect to the inputs. That will give you all the special derivatives because x and t are your inputs. Now, once I have phi Drake, when I have phi Drake, because I already have an underlying mesh representation, because those objects are defined in mesh, I know how to compute the residual without the need of having x and t as inputs. Right? So the input of that model is solely f. It just takes f. Right? All right. So I define here some hyperparameters, learning rate, number of epochs, and so on. And this is the training loop. I will run it while I describe it. My nightmare. Something that fails while I'm presenting. Okay, this never happened before. Let's see what, okay. I'm putting the test right now. So J is the physical constraint. Did I not execute the J? Oh, I didn't do it. Yeah, I was stupid. Yep, okay, let's. Oh, yeah, even the one before I didn't execute it. Hopefully, yeah, okay. All right, so let's just, that should work fine. All right, it runs fine. So those are the epoch, training loss, small L2 errors, and this is going to run for 80 epochs. In the meantime, let's analyze this code. So this is a traditional training loop. So I loop over the epochs. I set my model in train mode. I initialize my loss. I loop over the data set, like a batch. I take different batches over my data set. For each batch, what I do is I take the f associated, the different f functions associated with this batch. For each of them, here the batch size is 1, but in practice that's how it works. You have a batch, and then you push that through your model. You apply a machine learning model using the f, because that's the learning we want to map to learn. Edge index is the adjacency list. So basically this means I have the graph. I'm aware of the graph. And then it outputs the solution. So the solution of my PDE. Once I have that, I will call the phi Drake operation we discussed earlier. Remember, the phi Drake operation will take the solution, assemble, so evaluate the residual form, so basically my PDE. And then once I have that residual, I will implement the loss we discussed earlier on, this loss, right? So this will be the physical constraint that comes from phi Drake, which is over here, the small to norm, and this is comparing the prediction with the exact solution for my data sets. Right? So you have this kind of data-driven term, and then on the other hand you have this physical based term. All right, and then you backpropagate. You advance the step, which means like there's a one gradient descent update being performed under the hood, and then you evaluate to compute the error. Let's see what we get. Still running. So because this is on Colab, I couldn't afford to do something very expensive. So there's the mesh is coarse. The data set is everything but it's not realistic, not at all. But yeah, at least I hope it gets you, at least you can get your hands dirty with the code and kind of try to see what to do. So it will soon be finished. Okay, let's have a look to what comes after. I will execute the next cell. Yeah, so you can see the training loss and errors like diminishing nicely. So is there any question in the meantime on like what we've seen earlier, like in the notebook formulation or?
I have another question about the data. So say for the forecasting, for example.
Yeah.
In this case, it's simulated data, right? I guess for forecasting, is it?
It's also simulated.
It's also simulated. Could you put in real data if you had some?
No, there are two things going on. So one thing, so basically, when I passed quickly on those slides, when you do weather forecasting, you have two steps.
Yeah.
You have data assimilation, which takes real data, map that to a model of the atmosphere, an atmospheric state.
Yeah.
Right. Once you have that, that's where you use the PDE to advect to kind of compute the evolution from that initial condition.
Yeah.
To the next forecast, right? The GraphCast model doesn't tackle data assimilation. It does the second bit, right?
Yeah.
It does the bit that is usually done by solving a time-dependent PDE, typically something like Navier-Stokes, right? So that's why it maps from atmospheric, like from data created from simulations and not directly from observations,
Okay.
right? If you were to like, I think in this in the paper, like they plan to extend that to also account for data assimilation. But if you had a model that could also account for that bit, data assimilation, then you could in one forward pass map from historical data to the next forecast.
Yeah,
Amazing.
Yeah.
Those problems are very hard, very hard. The results of decades of research. People have been scratching their head for a very long time to,
And
to find.
data's noisy, observed data noisy, right?
Yeah. There are a lot of interesting questions. I was discussing one with my PhD supervisor recently. It's like when you have data-driven approach for weather forecasting, ultimately when it comes to things like rare events, your model will predict things based on the data it has seen, right? Not based on the physics, because there's no physics. If you are purely data-driven, there's no physics. Now, let's say in your data you have a lot of data and you only have a few occurrences of rare events. How can you be sure that when there's a real rare event coming up, how can you be sure that your model will be able to predict it, given that the number of occurrences is not that big, right? How can you?
Be biased by the.
Yeah. Okay. I think we're running out of time. So yeah, that's where also physics can be helpful because you can kind of encode more knowledge. All right. So we are done. Let's have a look at the solution. Okay. So it looks decent. It's not perfect. You can see that it's certainly not perfect. Kind of decent. You can see like this weird pattern. The error is 10 to the power minus 3. Yeah. So that's what we get. That's the solution. You can see there's kind of like some noise, strange things in the boundaries, but that kind of looks very close to what we did, what we had in the beginning, and then that's the pressure. Yeah, and I think we are now good. Yeah, so thank you for your attention, and if you have any question, I'm here to answer.